Alright folks, so let's look into this problem in much more detail. So we've got the steam pipe that's transporting some amount of steam from one point to the other. The pipe is constrained between two walls as shown in the diagram. We've been given some information regarding the steel pipe. So the external diameter measures 120 millimeters. You want to write that in meters, 0.12, that's up to you. And the internal diameter is 100 millimeters. We've been given some information concerning the steam. So we've been told that the initial temperature of the pipe is at 15 degrees, and when the steam enters the pipe, the steam is entering at a temperature of 200 degrees centigrade. So we're going to be looking at two situations here, and I'm going to add some additional components to this particular problem. So the original problem is telling us to calculate the thermal stress that's being produced by the steam in the pipe, and we also need to calculate the force exerted by the pipe against the walls. So in terms of against the wall, this is where it gets it becomes, at least from my perspective, subject to interpretation. I'm assuming that the question is looking at maybe the longitudinal component of the force that's going to cause some form of deformation to the pipe due to the steam entering it. But it might be worth also looking at, okay, what if there's some measure of constriction in the pipe? Do we also need to look at that in terms of how the pressure is going to cause some radial expansion too? So I'm going to look at this problem from two perspectives, just to have a clear idea in terms of what's actually going on. Now, there are other much more precise formulae that can be used, particularly when we're looking at analyzing stresses in cylinders and in spheres and things like that. But we'll look at that down the line. But for now, we're just going to use the fundamentals that we've learned at this point in time to try to get some figures in assessing the situation with this particular pipe. So let's crack on. So what do we know from the given problem? So as I previously stated, we've been given some information. Let me just write data here to define what we know. So we know that the initial temperature, let's call that initial temp, of the pipe, so let's call that TP is equal to 15 degrees centigrade or degrees Celsius. The temperature of steam, so the steam temp, let's call that TS. Okay, so that's equal to 200 degrees C. What else do we know? We've been given some information regarding the material of the pipe. So the linear coefficient of expansion, so that's alpha, that's equal to 15 10 to the minus 6 per centigrade per degree C. Okay. And we've also been given some further information regarding the material, so the Young's modulus, or the elastic modulus, that's the term by center frequency used, that's given us 200 GPa. Okay, so let's not forget that G represents giga, so that's 10 to the power of 9. So let's not forget that. So I think we've got all the information that we need to calculate for the thermal stress. So therefore, let's call this 1, the thermal stress. So let's characterize that as sigma T. Yeah. So that'll be equal to alpha times the temperature differential times E. Okay, so this is fairly straightforward. So this will be equal to, what is alpha? That is 15 times 10 to the minus of 6 times the temperature differential, so that'll be 200 minus 15, so that'll be 185 approximately. So again, the units will cancel out, leaving 200 times 10 to the power of 9. Okay. So as stated, that would be 185. So let's bring in our handy calculator to do the computation. So this would be 15 to the power of minus 6 times 185 times 200 to the power of 9, and that gives 555 times 10 to the power of 6 PA. Okay, and that is essentially 555 MPa. And there we have it. So we've worked out problem 1. So the next part is to work out problem 2. So problem 2, we're being tasked to calculate the force being exerted. So let's call that force, so let's call that the longitudinal force. So the longitudinal force. Okay, so let's characterize that as f of x. So f of x, okay, is equal to the thermal stress times the cross-sectional area of the pipe. Okay. So let's not forget that this came from stress is equal to the ratio of the force to the area. Okay, so that relates to this equation, right? Just to avoid any confusion. So what do we know? We haven't calculated the area, so the area of pipe is the area of the pipe. Let's call that A subscript P. That'll be equal to pi over 4. So let's not forget that this is a hollow tube. So we need to deduct the area of the outer section to the area of, or from the area of the internal bore of the pipe. So you can do it this way. So let's call that d external squared minus d internal squared. Or if you want to, you can work out the areas separately and work out the difference. Okay. So that'll be equal to pi over 4 into bracket. So this would be, so let's do this in terms of meters, just to save the hassle, right? So this would be 0.12 squared minus 0.1 squared. So that would be 0.12 squared minus 0.1 squared into bracket times pi over 4. And that would give approximately 3.455. Since we're still computing, let's do that to 4 decimal places. Times 10 to the power minus 3 meters squared. So we've got our information to work out what the longitudinal force is likely to be. Put that here like so. Therefore, the longitudinal force, we go to the stress. So the stress was 555 times 10 to the power 6 times the area 3.4558 times 10 to the power minus 3. Okay. So the force is quite large. Thus, when it comes to the design of this pipe, it's very important that a safety factor is provided to give the pipe enough thickness for it not to buckle or to fail during service. So we'll talk about safety factors down the line. Anyway, so 555 10 to the power 6 times 3.4558 times 10 to the power minus 3, and that gives 1917969 newtons, which we can then rewrite as 1.92 meganewtons. And there we have it.